Hi everyone, my name is Teja and welcome to this video series on a probability refresher for business analytics. So today we're going to look at the notion of sample space. Okay. A sample space, typically it's denoted as using this capital omega notation, is nothing but a set. It's a set. It's a set of, a set consists of elements. So it's a set of elements, and in this case we're going to call them outcomes. Okay, so sample space is a set of outcomes, and in fact it's going to be a set of all outcomes. Okay, so for example, if we flip a coin, we may land heads or tails or neither happens with almost, may not happen at all. So heads and tails are the all possible outcomes. There are only two possible outcomes here, heads and tails, right? So one interesting thing that we need to ensure is that these outcomes are mutually exclusive, in the sense that I cannot have both heads and tails as an outcome. Okay, so we're gonna build this set of outcomes where one of the outcomes can happen, but if that happens, nothing else can happen. And this collection of all outcomes that can happen is the sample space. Okay, for example, if you roll a die, maybe it has 6 sides, so numbers 1, 2, 3, 4, 5, and 6. And once you roll it, it will land on one of the faces, and that face is going to be one of these numbers. Okay, so these 6 numbers are going to be the 6 outcomes in this sample space. Okay, and before I describe, and so okay, so sample space, and I'm going to use, so sample space was a special name for a set, and outcomes are special names for events. Similarly, I'm going to use a special name, which is outcomes are special names for elements, and I'm going to use the special name event for a subset of the sample space. It's called an event. For example, the event could be land either heads or tails, and you know that that event is a subset because it is smaller than or equal to the sample space itself, which is a set. So that's an event. Okay. So for example, it can also be an event which is the event nothing, okay, or the null event. Okay, so null event is represented using the notation phi. I'm just going to use phi. You can use anything else, and everything event is just going to be the sample space itself. It's a set of all outcomes. So any outcome. So let's say you want an event which is a subset which has all the elements of your sample space. Then it's just going to be the sample space omega itself. And if you want an event which doesn't involve any element in the sample space, which is a set of all outcomes, then we just call it the null event. And this is true for sets as well. So there's this notion of an empty set or a null set, which is like a set without any elements. Okay. So given these two notions of sample space and event and outcomes, we can now kind of jump into at least like formalizing a little bit of what we call probability. And it's just going to be a way to encode beliefs about the likelihood or possibility of events, and events constitute of outcomes, so events are outcomes. Okay. In particular, so just to repeat, probability is just a way to encode encode our beliefs about the likelihood or the possibility of certain of outcomes. I mean, so there are many outcomes in the sample space. So for each outcome, maybe you encode a belief that what is the possibility that that outcome happens. Okay. So that's the, I guess, the English way of describing what probability is. And so generally what people do is they kind of want to say, okay, let's encode these beliefs. Well, how do we encode these beliefs? So let's follow some rules, and these are the probability axioms. Okay, and this is just a set of, I guess, assumptions or notation convention that we use, which is that first we're going to use this symbol P. So for simplicity, we're going to use the symbol P. So P bracket, and in the bracket we're going to put an outcome or an event there. And so here is the axioms. The first axiom is the we're gonna, so let's say probability, so omega is a sample space, so probability of omega we're gonna set it to be equal to 1. Okay, so this is a number, there's a belief that omega happens, sample space happens. So which just means that one of the outcomes in sample space happens. So we're going to ascribe this number 1. So an outcome happening from the sample space is 1. Okay, any one of the outcomes happening in the sample space. So we just need one of the outcomes in the sample space to happen, and that we're going to ascribe the belief that it's going to happen with probability 1. Let's say if we roll a die, one of the 6 numbers is going to happen. So the probability of one of the 6 numbers happening is equal to 1. Okay. Second thing is, for any set, let's say E is a subset of omega, subset or equal to. So this is the notation that I introduced in the previous video. For any subset, I'm going to use the probability of E should be at least 0. Okay, so I'm going to assign numbers which are greater than or equal to 0. Okay, so for example, think of this event, which is I'm going to get the first 1, 3, or 5. I'm going to get a odd number when I roll the die. So so I'm going to ascribe the my belief on and how likelihood is it that I'm going to get these odd numbers, or the event could be just the outcome itself, one of the outcomes. For example, what is my belief that 1 would land when I roll the die. Okay, so these two are the two axioms. And also, third axiom is that if I have 2 events, so I'm going to use E subscript 1 and E subscript 2 to denote the 2 events. So let's say there are 2 events, event 1, event 2, such that their intersection is empty. So for example, if the event 1 is 1, 3, and 5, and event 2 is 2, 4, and 6, I know that these two, the outcomes in these 2 events, the elements in these 2 events, they have nothing in common. So 1 is different from 2, 3, 4, or 6. Similarly, 3 is different from 2, 4, and 6, and so on. So the intersection is actually empty. Okay, so that means that these are called disjoint events. Okay, disjoint just means that the intersection is empty, and then my belief about them, which is E1 union E2. So I have 2 events such that the intersection is empty, then the union is just going to be equal to the sum, probability of E1 union plus probability of E2. Okay, so this is just another axiom or rule that we're going to follow. If 2 events are kind of disjoint, then my belief about their union is going to be my belief about the first event plus my belief about the second event. Okay, so this is the 3 axioms, and from which a lot of things follow. For example, we can we can deduce that since P of omega is equal to 1, P of phi is equal to 0. Because so phi is the set of no outcomes or nothing. So we're going to assign 0 to it because probability of one of the outcomes in the sample space happening is 1. Okay, at least one of the outcomes definitely happening is 1. Okay, so similarly, if I have an event E, then the probability of event E plus the probability of event complement is equal to 1, because E union E complement is equal to the event is equal to the sample space itself, because the set of elements and everything else, the remaining elements, their union is going to be the set of all elements or all outcomes, which is the sample space itself. So this is one thing which we can deduce. We can also see the probability of an event is going to be less than or equal to 1, because the probability of the sample space is 1, then E is a subset of the sample space. So we can see that, and all the events, for example, have to be, we know that this has to be greater than or equal to 0. That was one of the axioms in the previous page. So it will turn out that these numbers, these beliefs should be less than or equal to 1 for all sets. Okay, and in particular, it also means that since E is a subset of omega, or in general, if E1 is a subset of E3 for some two sets, then probability of E1 is going to be less than or equal to probability of E3. Okay, so if a set is smaller, if set of outcomes is smaller than a set of outcomes, another set of outcomes, and it's contained within the second set of outcomes, then which is this subset condition, then the my belief about the smaller set of outcomes has to be smaller than my belief about the larger set of outcomes. Okay. Yeah, and so okay, at this point, I mean, I'm going to wrap up this video. I want to say that these, I just introduced the axioms of probability, and probability are a way to encode beliefs of certain outcomes happening, and we define the set of all possible outcomes as a sample space, and defined the notion of events and looked at these axioms. These permeate many of the statistical treatments that you'll see of things, all the way from, let's say, linear regression to random forests to even deep neural networks. So it's very useful to have this good grounding of probability as a language to encode beliefs. Okay, thank you for watching.